Okay, audible? Okay, good morning and possibly good afternoon and or good night for at a good evening at some other locations if somebody is watching. Okay, so today I'll give an overview of the Indian summer monsoon. I believe it's not covered that much till now, especially its teleconnection perspective. And in particular, I'll be talking about some moisture flux phenomenon, like how moisture can impact that Indian summer monsoon. Some new ideas which we have in recent time. So mostly my work was really done by two of my PhD students, Priyankshi, who is in postdoc in Oklahoma, and Shikhar is planning to finish. And I acknowledge all other co-authors of the paper. It's not okay. Okay, thank you. So what I plan to do just cover largely three major topics. One is the monsoon teleconnection observation and models. That's I'll start with mean conditions, and then a recent discovery of a forcing for seasonal ENSO transition that finally impacts the global ITCZ, especially during boreal summer. And finally, if time permits, some ENSO monsoon correlation in seasonal prediction models that some kind of a paradox we'll try to address. So what I see here is this. The top panel shows the shaded is the rainfall during boreal winter, and where you have the large-scale ITCZ east-west oriented is in the southern hemisphere, possibly much closer to the equator compared to the boreal summer, which is in the bottom panel. And then we have this moisture advection or the moisture flux fields, which we will call F in this particular talk, where you have mostly convergence at the equator coming from the extratropics. And then here, depending on the location of the ITCZ, you have the convergence either in the northern part of the hemisphere or the southern part of the hemisphere, depending on the season, right? And the ITCZ goes little further to the north during boreal summer, and that gives rise to the monsoon over this India and East Asia, possibly, which is really at the edge of this moist ITCZ location, if the ITCZ is in that kind of a condition. Another thing to be noticed is this high in the Pacific Ocean as well as Atlantic Ocean. Look at this during boreal summer or boreal winter, where the southern hemisphere is in summer. We have there is a high here, and this is Pacific high. Northern Pacific high is at this location during boreal summer, and also we look at this northern Atlantic high at this location, and this has large role to play, or a very important role to play, to anchor the location of the ITCZ, especially when in terms of its zonal asymmetry. So in other words, the zonal location, the east-west location of this high can anchor this location or move this location of these maximum cloudy zones and rainfall at during different years. And even recent observation suggests that this movement also can change the interseasonal variations of monsoon over East Asia as well as possibly over India. Okay, so what about the internal variations? The internal variations of this rainfall, now I speak to the only boreal summer, is here. And then most of the variations or the highest variations are seen near the equator and need not be over locations. See if I go back here. So need not be over locations of highest rainfall. For example, over Bay of Bengal, we have the rainfall is much larger. The relative variations compared to the equatorial Indian Ocean, especially eastern part of the equatorial Indian Ocean, over Bay of Bengal, the variation is not that large. Okay. Similarly, over the East Pacific Ocean, where the region of most El Nino or ENSO location, the variability is much larger. And when we talk about, now I have taken a box here, so there's a much more, this one here. So if I take a box here, and if I divide this box into two parts, and just make a plot of the mean precipitation over that region at every grid point, and in the y direction, if you plot the y-axis, if you plot the interannual standard deviation of precipitation, and the shaded locations are basically the moisture flux zonal component or meridional component of the mean moisture flux. So in overall, what we found out, what can be see is that to the western side of this region, that is Indian region, not the West Pacific Ocean, over the Indian region, the mean flux, zonal flux is high, with rainfall standard deviation is low. However, over the West Pacific Ocean, the mean rainfall is lower, or the flux, zonal flux is lower, but the precipitation standard deviation, internal standard deviation is higher. However, when you go to the meridional flux of the moisture, over the western region, that is over this Indian region, the mean is large. Again, the standard deviation, precipitation standard deviation is low. This is the same thing. However, in the eastern side, the West Pacific Ocean, both even the standard deviation of the flux is also high. In other words, what I'm trying to say is that the internal variations of the moisture fluxes over these two regions need not go along with the internal standard deviation of the rainfall over both the regions. Okay, so neither the means nor the internal variations of the fluxes go along with the internal variations of the rainfall over these regions, and therefore it has to be that the mechanisms of the internal variations would be very, very different. So now we go focusly only over this Indian region here. So this is the bar of the Indian summer monsoon rainfall, IISMR we keep calling, and so it will keep coming back here. So this is the anomaly of IISMR in terms of percent. The mean is about 7.2 millimeters per day, millimeters of rainfall per day. And then there are so many drought years, which are in red, and so many flood years, last 120 years, so which are all blues. And then these red dots are the El Nino years in summer, and the blue dots are La Nina years in summer. And you could see that there are occasions of floods without La Nina. So usually we will have floods with La Nina and the droughts with El Nino, which are coming back. But there are several floods without La Nina. There are several droughts without El Nino, like here. And there are even normal rainfall with El Nino, like here. Or even there is a flood with El Nino, I believe it's 1994 or 1994, floods with El Nino. So this is a box plot of this same rainfall, this here. The green line is the mean and the orange line is the median. So the median is to the top of the mean or the right side of the mean. That's basically suggesting that there are far more droughts than floods, or more stronger anomalies, negative anomalies than the positive anomalies. Okay. Now, if we do a power spectra of this rainfall, I have used two different data sets just for a consistency. So you look at, there are highest variance you see at the 2 to 4 year time scale, quasi-biennial time scale, 2 to 4 years, not with the ENSO forcing. This is could be understood as the ENSO forcing, about 4 to 8 years here. And then there are other variations, a multi-decadal variation as about 50, 60 years. And there are like 16, 15 years of variations. And if you look at the spatial map of such variations or the variations of the rainfall at different grids, you notice that the quasi-biennial variations and the decadal to multi-decadal variations have the highest variance over the Western Ghats as well as Central India, not the ENSO variance. So this Central India variance, if you go back to the winds and the moisture flux, so that usually moisture comes from the Arabian Sea, which actually takes a turn, which from the easterly winds at the equator takes a turn here at the Somali location because of the heating over this region. There's a Gilles response here and comes and hits these locations. And even there are mountains here, so you get highest rainfall over the western parts of the Western Ghats and the western parts of the Burmese mountains. And then these winds take a turn here because of the low over this region. There is a monsoon low, it is termed as, and in fact, the winds at this just south of the Himalayas is kind of southeasterly, not westerly. So most of the moisture comes from the Arabian Sea, but most of the disturbances or the synoptic scale disturbances for the Indian monsoon actually originates over the Western Pacific Ocean, moves westward, and then generates the depressions and lows over the Arabian Sea, and then they move further over the Indian region, right? So we need moisture that's coming from the west, but the dynamics, the systems that the moisture should be converted to the rainfall, that dynamics must come from the east, okay? So thus, this, to have a mean monsoon, the way we look at, we must have both these conditions correct. For example, a model that needs to make this mean reasonably well must simulate the western parts as well as eastern part well. Only one part won't help. Okay. Now, how does it make this internal variation? Mean, what is the mechanism? What it is a simple linear correlation of the Indian monsoon with the sea surface temperature everywhere. Okay, so the highest correlation is in the equatorial central Pacific or eastern Pacific. This region is an NO 3.4, and this is a correlation is more than 0.4 here. And then this pattern is remarkably similar to the ENSO pattern of the Pacific Ocean. So if you take just the SST without anything, like you do not connect to the summer monsoon, the first UF mode is remarkably similar to that. It was not necessary to be, because we know that ENSO could possibly persist in a model or could stay in a model even without the monsoon, maybe. Okay, but just because if you just give the wind forcing in a model, you should be able to get ENSO, it is possible. But this pattern is remarkably similar to this. What does it suggest? It possibly suggests that in a real world, there must be an interaction. Okay, without interaction, it is not possible. That is one way, it is not possible, because we know ENSO has its own dynamics that need not have the monsoon forcing. At the same time, monsoon has its own dynamics and moisture modes, which need not have the ENSO forcing. But this similarity suggests that there must be interacting with each other. Without that, it is not possible. Okay. Now, since this relationship is so strong, it is almost impossible to figure out the impact of other ocean basins like the Atlantic or the Indian Ocean from this particular picture. So if one regresses out the SST, from the SST, the rainfall variations, internal variations of rainfall, and then further, regresses out the NO 3.4 SST, NO 3.4 SST from these SST variations everywhere, and then the regress again or the correlate again with the Indian summer monsoon rainfall, then you find this. So in other words, if you remove the ENSO impact, you are to get popped up these Atlantic oceans. This is the Atlantic Nino region, and a negative anomaly impacts the rainfall in a positive way. For example, Indian Ocean, the central equatorial Indian Ocean mode, where the positive values of SST impacts the rainfall in a positive way. North Atlantic, again, it pops up, but may not be that, for example, a tripole of the Atlantic tripole, although it is here. Interestingly, it is here as well as here. Okay, so now, we look at a few characteristics of ENSO. This is the time series of Nino 3.4 SST during the last, whatever, 50, 80 years. And I have picked up, I have also written down these droughts and floods. Again, the same story. Need not all the El Ninos, which are here, need not have droughts, and all the La Ninas need not have floods. Now, if we look at the time series of, or the power spectrum of the ENSO, the 2 to 4 year mode, which was found in the ISMR, inner monsoon rainfall, is present here. It also has this 4 to 8 years, or very close to possibly 5 to 6 years, and about, say, 30 years or so. Okay, so the multi-decadal mode of the ISM, or Indian summer monsoon rainfall, is not present in this particular thing here. And then a relationship of the Nino 3.4 SST with rainfall everywhere, it looks like this. So what happens is, this is the change in the water circulation, or the change in the intensity of the water circulation makes this, an El Nino makes more rainfall here and suppressed rainfall over this region, as well as over the Indian region. And the convection over this region that can drive over this, the rainfall over India, possibly could change or suppress the rainfall over India during an El Nino. So that was kind of a theory for several times, or several years, but we'll kind of try to revisit it. So do a scatter plot of Nino 3.4 SST anomaly with ISMR. For last 120 years, it looks like this. So you call it a good relationship or not is up to you. So this correlation is about 0.57, and with a slope of minus 0.6 millimeters per day per Kelvin change in the SST. Some of the years, important years I have marked here, like 1972 or 1918 as the very strongest drought ever. There are many years like this, possibly 97 and 84, 94, with a strong El Nino, there was no flood. Sorry, no drought here. Even there are several floods here, even with a very, very weak negative forcing, or there are almost no forcing, right? So in summary, this is in percent, the total droughts, 21% of the total droughts of the rainfalls, out of the 21%, El Nino can explain 50% of the droughts. Rest are neutral, either neutral or for the La Nina years. Similarly, for the flood, only 56% of the floods can be explained by the La Nina, and the rest were due to El Nino or during El Nino or neutral. So ENSO again cannot explain all the droughts and floods. Okay, not just that, it is fine for this one. The scatter possibly is little too much here. Okay. However, even today, for the seasonal prediction of the rainfall, possibly this is ENSO is the most important deterministic factor or the predictor. Now, if you do the same thing, just change the plot here, and then just color those years with different symbols, like for example, for those now for the preceding winter, that last December, January, February, if it was a La Nina, we make it blue, and preceding winter was an El Nino, we make it red. Okay, and then if the SST from the preceding winter to the current summer has increased, and Nino 3.4 SST, make a triangle which is up triangle. So in all those steps, okay. So what you see here, the scatter remains same, but suddenly many blue years, that is when some preceding winter was a La Nina, possibly came to the lower side of the spectrum or the scatters, and the many red years has gone to the upper side of the spectrum. Okay, that basically suggests that if the previous December, January, February was a La Nina, even with the same value of summer SST of Nino 3.4, you are likely to get a weaker rainfall or the lesser rainfall compared to if it was an El Nino, coming from an El Nino. So Not just that, you look at these years, for example, 2002, without an El Nino, there was a drought, and the SST, there was an increase in SST from the last winter to the current summer, like all this last winter to current summer, even with a weak El Nino, just above 0.5 Kelvin. There's a very strongest drought came when there was an increase in the SST from the last winter to the current summer. So in summary, what you're trying to say is that it is not just the current summer's sea surface temperature that drives the monsoon rainfall, but it is the evolution of this sea surface temperature of Nino 3.4 that in turn has an evolution of the entire atmosphere in terms of its winds as well as moisture that drives the rainfall. So if you start from a colder state and you go to a warmer state, you are much more likely to have a stronger drought. And if you from a warmer state to go to a colder state, you are likely to have a weaker, or possibly the drought may not come that strong, or you are going to likely to have a larger, stronger monsoon. Okay. Now, this is summarized here that, for example, DGF La Nina to this is x-axis is a JJS Nino 3.4 state, and this is so these two bars are for El Nino, and these two bars are for these two bars are neutral conditions, current neutral condition. This is current El Nino conditions, and this first set of box plots are for the DGF La Nina conditions, and this is DGF non-La Nina conditions, and again DGF La Nina conditions. Look at that. Even if you have currently you have an area, in the current summer is a neutral condition, a DGF La Nina could had a more weaker rainfall compared to other states, and especially here when DGF La Nina is negative or negative DGF it was La Nina, it was a much stronger rainfall, stronger droughts compared to the DGF this one condition. So you are likely to have a stronger droughts with when you come from a winter which was La Nina. So what could be the mechanisms? There are several mechanisms, those were proposed earlier for the impact of ENSO on monsoon. For example, here ENSO can impact changing the Hadley cell. Then IOD, the Indian Ocean Dipole, can have an impact of an ISMR. Atlantic oceans, especially I'm talking about the equatorial Atlantic Ocean, can have an impact with different mechanisms like Gilles type quadruple response, modulation of Asian jet, and then Kelvin response into the Indian Ocean that comes from the Atlantic Ocean. For the ENSO case is like a Walker circulation change, middle tropospheric temperature gradient that changes the tropospheric temperature gradient over this region. For this regional Hadley circulation that in turn is interconnected to the Walker circulation here that changes the regional Hadley circulation, and possibly the preceding winter ENSO. Then even at the interdecadal time scale, there are several theories. Okay, so again, the summary of those theories are here. This Walker circulation change due to ENSO or the Pacific Ocean basins change in the SST gradient, and middle tropospheric temperature gradient is here, and this Walker cell, and that connects to the Hadley cell, local Hadley cell over this South Asia. This is connected to here, and possibly the preceding winter ENSO condition is connected to here. Okay, now the problem is that with all these different theories, that the diverse approaches, that impossible to quantify relative impact of tropical forcing on ISMR through a single mechanism. That some forcings they're talking about dynamics, for example, change in the upper level velocity potential, right? That finally connecting even if you quantify the change of the upper level velocity potential, how do you convert that quantification to the change in the rainfall, monsoon rainfall, is not clear. Even it's never done. Okay. Similarly, when you're talking about the change in the gradients of the upper level or the mid-level temperatures over at this location, again, the change in the temperature gradient need not necessarily or it's not easy to change that or convert that parameter to rainfall. So many other theories are very simple, very like that. Even Gilles type quadrupole response, there is no easy way that you quantify it to finally say that this will be the impact on the rainfall finally. Okay, so to take a first step, we thought we'll do something or we'll try to go to the moisture. But before that, I think we should take care of this. It is not that there is no simple model does not exist. There is a nice simple model exists for the rainfall over in the tropics, which is done quite a long time ago now and kind of getting popular today. That what he did is that he wrote the moisture budget or the moisture imaginary budget equation based on Nilian and Hale and simplified, and he wrote the rainfall minus evaporation over a column of the atmosphere in this simple form, where the energy available to the atmosphere is QDIF, that is the energy available at the top of the atmosphere as well as the surface, the total energy available to the atmosphere. That's divided by some stability parameter C divided by this total column water vapor over at the column, the ratio of these two, and -1. So this energy available at the top of the atmosphere or at the atmospheric column can be amplified by this denominator, right? Usually the values of C, which is here, which is actually very close to that value of the P word. Here, look at that. The C is slightly more than about 1.5 times or 1.2 times of the total column precipitable water, which is W here, which I'm talking about. So this term is less than 2, more than 1 most of the time, but thus can amplify this condition. And this being the total column moisture convergence kind of suggests that there is a large scale circulation that can drive this moisture convergence and then can get amplified by this local stability as well as the moisture availability over this region. So this scatter plot shows how this QDIF is a function of the precipitation minus evaporation. Now, all these years are, the blue years are the El Nino years and the red years are the La Nina years, similar here and as well as here. So, although the highest correlation or highest relationship between the P minus E and the rainfall P minus E and one of these parameters is in the stability condition, there is no apparent relationship. There is no apparent relationship between the El Ninos and the La Ninas on these parameters. There are certain variables, like for example here with the higher amount of P word with the La Nina it could be something, but I would see these blues and the red dots are almost kind of everywhere. So it basically suggests that the variations in the P minus E is a combination of all the three parameters and need not be coming just from one parameter dominantly. Okay, so it is not a predominant of one parameter, but at the internal time scale at least, a combination of the three gives us the variation of the P minus E. Okay, so now let us come to the total precipitable water. So just give a background here. In April, before the summer monsoon starts here, so this is the total column precipitable water over this region. This is very dry over Indian region, and the West Equatorial Indian Ocean is wet here. Now, come June, kind of enter Indian region, this region, South Asia is covered by monsoon, possibly here almost up to this region, and Bay of Bengal is very wet. July, it's even more wetter, and then by September, it starts retreating. However, water vapor stays over this region. Okay. Now, the flux of moisture, which is in these arrows are this climatological flux of moisture here. We take this box, and this is the hatch region, is the Indian rainfall region, for example. So this is the climatological flux. This has to be remembered. It comes from the west. Even over this region, that is, so basically it comes from the west and goes here. But the total incoming flux of moisture from the Arabian Sea exceeds the amount of moisture that goes out of this region. Okay, so that makes the convergence of moisture. That is the basic mechanism of convergence of moisture. There is a flux of moisture from the south as well, but that's much weaker, very, very weak. Actually, 1/5 of, I believe, maybe about 1/5 of this flux. So this kind of the FW, which you call it here, minus FE, is basically should give you the convergence of moisture flux over this domain. And if you just do a simple calculation here, and if you do it here, you will find that A is the area of this domain, and if there is a F net, you can write it down here. For a seasonal average, seasonal mean, if del P or del T goes to 0, then you can show that the F net is a function of the P minus E, and that's the kind of is here. So basically, this is Indian summer monsoon rainfall here, and this F net here, and kind of to some extent a linear relationship, because we are in a smaller range of the F net domain. If you go to a larger domain, like from the winter to the summer, this should come to an exponential fit from the closest cluster, this one here. I'm not going to go to this one here. Now, what drives the F net? Therefore, since FW, that is the flux from the west, and FE, that the flux from the east, we have identified to be the most important ones. We can show that the FW is a linear function of the PS1 minus PS2. That is, PS1 is the surface pressure, which is here, and PS2 is here. The background shaded is the climatological surface pressure. Okay. So basically, climatologically, this region has a lower surface pressure than this. And again, this region also has a lower surface pressure than this. However, this scatter suggests that if you can decrease the surface pressure over this region or increase the surface pressure over the equatorial Indian Ocean, you possibly will have a stronger winds, and that can drive stronger moisture if moisture is available. Similarly, for this eastern side of the domain, that if you have a higher surface pressure compared to here, you will be driving out more moisture from the domain, right? So thus, we should be able to now divide, or we should be able to diagnose these internal variations of moisture over this domain just from these surface pressure anomalies over these 4 regions, right? So that is the first step. Okay, so then let me not go to this. So what happens during the summer, during our summer, during La Ninas and El Ninos? So this is the during La Ninas, and this is the background is the moisture flux anomaly. So look at this. This region, which had a climatologically lower values of surface pressure, dips even further. It is not over the equatorial Indian Ocean. There is a dip in the equatorial Indian Ocean also, but this dip in the northern side is more. That drives stronger moisture eastward. At the same time, you get this region also a lower value, so that you get these anomalies, anomalies from the east also. So basically, this suggests that. So basically, this suggests that the outgoing moisture flux is less here at 90 east. Incoming moisture flux is large here at 70 east. For the El Ninos, the outgoing incoming moisture flux decreases at 70 east, and the outgoing moisture flux increases at 90 east. So for El Nino, if you start, there's a divergence of moisture because of anomalous decrease over this region and anomalous increase over this region, right? For La Ninas, the anomalous increase here is of the same order of the anomalous decrease here, I'm sorry, the anomalous decrease of the outgoing flux is of the same order of the anomalous increase during El Nino at 90 East. However, the increase in the incoming flux is not as much as the amount of decrease during La Ninas. So, sorry, during El Nino. So, my point is look at the asymmetry in the flux convergence during El Ninos and La Ninas. So, although we look at in correlation analysis, we look at them like a symmetry, but correlation does not understand the asymmetry. But in real life, there is a huge asymmetry between these two in terms of at least the mechanism. So then how does the preceding winter's El Nino versus La Nina conditions impact this? I'll just go to this particular figures, nothing to, this is all the details are here summarized here. Aiding like previous winter's La Nina, which had a weaker rainfall, was because of the decrease in the incoming flux here, and the weaker last winter's El Nino, which had an increased rainfall because of the decrease of outgoing flux here. So suggesting that if we come from a La Nina from the previous winter, the western side is more active. And if we come from an El Nino in the previous winter, the eastern side is more active. And the eastern side more active possibly suggests that it will be more connected to the current summer's ENSO condition. Okay? Like now, if you look at for the IODs, unlike for the ENSOs, if you look at for the IODs, these flux anomalies are in the one direction, like for example, positive IOD, right? Not for the negative IOD. So for the positive IOD, for example, the incoming flux increases, but the outgoing flux increases even further. And that gets compensated by the incoming flux from the southern boundaries, and that gives rise to an increase in rainfall. So this is only, IOD is the only equatorial SST forcing that had a strong perturbation at the southern boundary. Okay. Now, for the Atlantic Ocean, again, the anomalies are in the one direction, right? So my point is, this arrow and this arrow, that is that anomalies in the both east and west of the Indian region of the same direction, versus this here, where the anomalies in the west and east are exactly opposite direction, right? So what does it suggest? Possibly that, go back here, what basically suggests that now for the rainfall, for the monsoon rainfall, there is a heating here, strong heating, and strong heating should give you the Gilles time response to the west as well as to the east at different ways. And given that during El Nino years, these responses are opposite to the opposite sign to the east and west, possibly suggests that during El Nino, this region is self-sustained, or it's it's aloof from the outer world. Okay. However, during La Nina, when the heating, Eastern Pacific heating is much closer, then this asymmetry decreases. Similarly, for example, IOD for the Atlantic Oceans, the forcing is much more symmetric and possibly much more larger scale. In other words, what I'm trying to say is that the Indian monsoon is possibly, once the conditions from the ENSO is set up over the Indian region, possibly based on the availability of moisture, the monsoon is much more self-sustained or the localized over this region, right? And it doesn't talk to the other regions. And possibly that is also the region during a strong ENSOs, the impact of the other ocean basins are minimal. All right. However, when ENSO is weak, it responds to the other ocean basins in a much symmetric way because it is far away from the Atlantic Ocean, for example, right? The response is in the one direction. It looks like it is just a part of the system, and depending on the other conditions, right? And there is an interaction, or at least the forcing of the other ocean basins to this region. Okay, so then how good is this in the, now we just look at, I think I will not go to the other reason. How good is the CFS-V2 model in capturing this? That is the model which we use for the forecasting kind of over for this region. So this is again observation El Nino drought versus CFS-V2 El Nino drought. Look very, very similar. So look at here. So that in observation, we have seen that is a incoming moisture flux to the observation, this FW is much lower, and outgoing moisture flux is much higher or not as much. CFS-V2 both are very, very similar to each other. Okay, so, and then for the El Nino drought are for this one. So this is also is here. So in summary, if I come here, in summary, what we found is that for this particular model, this, if you just show it here, this is for the end, all that, this is for the observation. This is a moisture flux of 70 east and inner summer monsoon rainfall. This is observation, positive correlation. For the CFS-V2 here, correlation much weaker. So the model does not respond to the east-western parts of the Indian Ocean or Indian region. For the western side, sorry, for the eastern side, it's a 90 east, where this relationship is to the negative slope here. This has a much stronger negative slope here, right? So suggesting that the model is much more sensitive to the moisture flux at the eastern boundary. So finally, if you subtract these two, that's FW minus FE versus ISMR, you get a much stronger relationship in the model because of this strong relationship here and not here, right? For observation is a little much weaker compared to this, right? So the fluxes in the model drive the rainfall more stronger, but mainly because the flux to the eastern side of the domain compared to the western side. So this is back to the observations now. This is the ENSO conditions, El Ninos and La Ninas. And then finally, if you can just try to summarize this is ENSO, this is a surface pressure anomalies in shaded. For ENSO conditions, drought minus flood, what will happen is that to this region, there is an increase in the PS here that kind of decreases the FW. And to the Western Pacific Ocean, Northwestern Pacific Ocean, there's a decrease in the PS compared to the equator, there's increase in FE. So this finally, these two together decreases the net flux of moisture over this region, decreases the amount of water vapor availability over this region and decreases the rainfall. However, for the non-ENSO years, droughts minus floods looks like this, where you have a high here, increase in the PS here, but not as high as for the ENSO cases. There is a decrease in the PS here, also decrease here, but finally this, since the decrease in the equatorial Indian Ocean is more, FE increases, that is flux increases, FW decreases even further, and finally there is a decrease in the FNet, and thus a decrease in the rainfall. The difference is here there is a divergence. This is a divergence because of the opposite signs, and this is a divergence of the just the zonal shear. Okay, so this I think maybe we'll just, what happens in the CNIF6, just quickly I'll summarize for the CNIF6 models. CNIF6 models, what happens is that over the Bay of Bengal, there it is the decrease in EMFR over Arabian Sea is correct, but what the observation is here over this for this region, but the Bay of Bengal, this flux is actually CNIF6 model is wrong. And maybe I'll just stop here. Do you have more time or some more? Or it's okay. 5 more minutes. Okay. So now maybe I'll just go to this particular. This is here. I'll just show the second verse. Quickly, I'll finish this and sorry. So this we have looked at the model, CFSB2 model, and we showed that the model is very, very sensitive to the moisture fluxes to the eastern side of the western of it, right? And that kind of suggests that it will be very, very sensitive to the what is happening to the Pacific Ocean. Okay, not to the Atlantic Ocean or to the eastern to the western side. So several of those models, like here, there are seasonal predictions. We look at that rainfall correlation between the Nino 3.4 SST anomaly and Indian summer monsoon rainfall. Most of the models has a much stronger relationship compared to the observation. So observation will change depending on the time period. It can even go to 5.7. But nevertheless, the models have a much stronger relationship to the ENSO compared to that in observed. Okay. Now, we try to look at this in a slightly different way. So usually all these dynamical forecasts are ensemble forecasts. Okay, so we start from different initial conditions or different physics, and we start at a different analysis, and then you go to the forecast domain, and so this is the forecast here, and finally all these are averaged. This is the target season. These are all averaged. So the path it takes depends on the particular model's mechanism, how that mechanism is working, right? So the path it takes here. So finally you are looking at here, we do not look at the path. Neither we look at that why it has reached here, even at this location. The forcing that is determining that location or this phase space at this phase space could be different at different ensemble members, right? So we try to understand this by an ensemble simulation of the same model, CFS model, but from two different sources, so that we are just kind of independent. So we have 38 years of simulations and 5 ensembles each and every year, and the seasonal simulation, right? So starting from whatever that initial condition is, and then you go up to this June to September season. So since all these ensemble members are independent of each other, we can consider them as 190 years, basically 190 realizations of this kind of seasonal condition. So the ensemble mean, how do you make ensemble mean? For a particular year, we take all these 5 values and just average over the 5 values. That's the ensemble mean of any quantity, isn't it? So we have individual members here, and you have ensemble means here. Ensemble means are 38 values, and ensemble individual quantities are 190 values. That's all, right? So now, if you plot this, make a scatter plot between ISMR and N34 into observation, it looks like this is about correlation is 0.5. And you take all these 190 members and plot here, it looks like this. Correlation is 0.55. Okay? But the moment you use the ensemble mean, you look at this, correlation is 0.7. What I'm trying to say is that the ensemble means correlation or the relationship between Nino 3.4 and ISMR is far stronger than even in that model's individual members, right? So this is, as I said, there are 2 different versions of the model we have used. So this is the observation, and this is the first version of the model. This E all members suggests that all different members like this here, and EM is the ensemble mean correlation. So this ensemble mean correlation is stronger in both cases than the individual members. Okay, so why is that therefore? Why ensemble mean can increase the ENSO monsoon correlation or the correlation or the impact of ENSO on rainfall compared to what is present in the model? Because I would guess this is the actual model, right? This is individual members of the model, individual physics in the realization. But moment we make it means, and you are getting something very, very different. So we have done a kind of an bootstrapping and few other steps. We see that for many of those members, like the means, this is observation, ensemble mean again here, and the individual members are here. So if you take one of the 5 members. Individual members correlation is not as high as ensemble member. So this is a spatial map of the same thing. Observation, this is a correlation of the Nino 3.4 versus rainfall. This is an observation. This is the ensemble mean, again, in the model, and this is individually 5 members. Look at that. None of the members show as strong a relationship as in the ensemble mean, right? So this is far more homogeneous and strong compared to the individual members. So just averaging this and having getting the correlation gives you this. So to further understand that, we did a simple analysis. I'll just take 2-3 minutes. Okay, simple analysis. So imagine that in year 1, that one of the first target year, Nino 3.4 has a positive anomaly. In member 1, member 2 positive anomaly, member 3 positive anomaly, negative, and then positive. So basically, four of the 5 members was kind of an coherent or something like gave the same sign of the anomaly, right? That is the ENSO forcing. So we push it to the 4th bin. So basically this in this bar, this is the 4th bin here. Okay, so 1 year like that. Now year 2, all of them are negative. So all the members agree with each other, and then that comes here, right? So we go to year by year and do that calculation. What we find is that in the model, the 5th bin is the most populous, okay? So basically suggesting that almost all years, all the 5 members agreeing or that their anomalies of Nino 3.4 is same, either positive or negative, doesn't matter, okay? However, when you come to only 3 members or 4 members agreeing with each other, the other 2 or 1-2 members are not agreeing with each other, very few. There is nothing, never happens as actually these 2 are, because these are 2 is basically 3 and 1 is basically 4, right? Because they are complementary. Okay, so now if you average these 5 members, because we have when you are averaging the 5 members for that particular year, the forcings from the 5 members gets dominated because you have the ENSO forcing is very, very strong compared to the forcing from the other ocean basins, right? So if you look at this Atlantic, for example, if I do the same thing for the Atlantic Ocean or Atlantic Nino, only about 50% of the members agree with each other. In other words, if the Atlantic Ocean is positive or negative anomaly during a particular year, only 50% of the members will agree with each other, okay? Most of the members will disagree. So, in other words, even if in the model, the teleconnection between the Atlantic Ocean and the Indian Ocean is correct in individual members, when you average all these, it will decrease or it will diminish the impact because many of those members are not even agreeing with each other. However, if you come to ENSO, since most of the members are agreeing with each other, it retains the relationship. Okay, as not just that, ENSO's impact is stronger globally, right, compared to the other ocean domains. And both this together makes the ensemble mean correlation much stronger compared to the individual members correlation. So what is the takeaway message from here? We're just trying to say is that it is not that the models do not have a correct teleconnection of the ENSO or the other ocean basins. We really, when we have to understand these teleconnections or diagnose a model, is better to be very careful, especially when doing the ensemble averaging. Okay, ensemble averaging can remove the actual physics of the model. Okay, so that has to be very, 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 very carefully seen. Okay, just without, without taking it as granted. So I'll stop. The other part I will not do because that will take some time. Okay, thank you.
There is enough time for questions.
Okay.
Hello, this is Shomodeep from IIT Bombay.
Okay.
So I just wanted to ask that in the one of those plots, you have also shown the contribution of eddies. I think for that box in Indian, the flux divergence, and there was mean, there was eddies and different El Nino La Nina, which shows very negligible contribution for eddies.
Right,
now,
right.
Now I want to ask that as you have done composites for every different El Nino and La Nina years with flood and drought, was that eddy again seasonally averaged? Or
yeah, ADs were calculated for every season separately, and then they were averaged for like this, right? That's what you're talking about, isn't it? Right?
Yeah.
So ADs were calculated every season separately, and then they were averaged for this particular years. Okay. So they don't go to zero, right? Because these are only subset of that total.
Okay. But like when you're calculating transient eddies, doing a seasonal average wouldn't by default make it really less. Well, what I'm trying to say is if we look into the something similar phenomena in a more transient time scale, like instead of flood and drought, let's look into something like active and break. Yeah. Do you think eddies will matter more?
Yes, yeah. Obviously, yeah. Okay. But at the same time, I should tell you that even in that during active break cycle, the variations in the total column water vapor is far less compared to the rainfall.
Yeah.
Okay. So the active break cycle may not be the only function of the amount of water vapor. So water vapor will drive the seasonal mean more than the active break cycle. Okay. So active break cycle will have more, dynamics will have more role to play in the active break cycle. So that way, this is more, little more meaningful here.
Okay. Yeah. Thank you.
Yeah.
So the results with greater impact on precipitation having a La Nina or El Nino in the previous winter got me wondering about things like the land surface. Is there any memory in the land surface or any effect from Tibetan snowfall or anything like that that could help some of this?
Actually, we have done that. It is the it comes out to be the change in the seasonal cycle, not the land surface processes, because when you have for example, you're starting with some strong ENSO condition here, the southern hemisphere and the northern hemisphere, the ENSOs are, because say boreal summer, southern hemisphere will be a very different condition compared to the boreal winter, right? So to have an ENSO impact on the rainfall, usually it requires a symmetric behavior in the north and south. Okay, so what we have seen is that the seasonal cycle gets delayed or advanced when you have a strong winter ENSO. So that can change, or that changes this circulation pattern, and usually we'll have those impacts of the previous winter's condition entry impact during the early part of the season. So it is not at the latter part of the season, but you will have the impact of the early part of the season.
I have a question.
Yeah.
So it seems that to the flux from east or west really matters, and it's controlled by the meridional pressure gradient.
Yeah.
So the heating warming pattern or low surface, high surface pressure pattern, is it controlled through some stationary wave type of a mechanism, or do we understand what anchors low pressure versus high pressure pattern east west?
Yeah. So this, to the eastern side, it is mostly governed by this Pacific Ocean's the conditions, and several times it is the El Nino. That's the reason in the CFS V2, for example, in the models, which is far more this one, you will find that this is the FE that governs. Western side, I'm not very sure how exactly. I'm not very sure, because part of it is just a response to the heating over this region. So this is really not completely independent of the heating or the rainfall over Indian region. Yeah.
Right. Because in your other work, you show that surface pressure anomalies over the Iranian plateau and Afghanistan, they matter, but this particular signal is over northern part of Arabian Sea. So that I find that a bit surprising that I thought it would, the same region would pop up in terms of surface pressure.
So no, but please note that the other work with that was related to AIM. So that was in month of May. All right. So it was much further to the north. This is during the monsoon season where it comes much closer to the equator. So it just propagates. Yeah, that was in May. Yeah.
All the more reason to study that region actually as to what really controls that. I mean, that region is quite, non-convecting throughout monsoon season, I believe.
Possibly, yeah.
So, but still controlling as much monsoons.
Yeah.
Thanks.
Okay.
When looking at the relationship between ENSO and ISMR, I think you showed at some point that the tendency of the ENSO index mattered somehow most, that the actual current ENSO index.
The tendency,
the
right?
tendency, exactly, the tendency mattered most, the derivative of time. And so in this case, is there a delay time scale that pops up, a particular delay time scale between the ENSO index and the ISMR? That would explain why the tendency is related more than the current value?
And the problem with the calculation of tendency is that tendency itself is dependent on the current value. Because that's right. So I'm not saying that, so it is the current condition that sets up possibly the mean. If there is any mean, I mean, I'm not very sure if there is any equilibrium condition when the seasonal cycle is always changing, right? So, but given that, like within the season, but the tendency is only kind of modulates it. Okay, the current condition still is dominant forcing, but the tendency is just a modulation to that.
Let's thank Professor Chakraborty again for a very nice talk. I think it simplifies all the teleconnections into east-west fluxes. I quite like this. Yeah, thanks.